Hey students, we're going to start a new chapter today. This is chapter 7, and it's actually kind of a short chapter, and so this will be a fairly short lecture. I just want to cover this one chapter, and this gives us a chance to kind of get caught up. I don't want the lecture to get too far ahead of the homework. So this chapter is called Generating Sets. Generating Sets. And here's the idea. We talked about a single generator for a cyclic group, and what we want to do is sort of generalize this idea. Now we're going to start with a theorem that's useful in its own right, but it'll also be connected with this idea of generating sets. So theorem 7.1 goes like this. Let's take a group. So let's say if G is a group, and we have some collection of subgroups of G. So let's say H sub alpha, where alpha runs through some indexing set A. So if this is a family of subgroups of G, then, and here's the punchline, the intersection alpha runs through script A of H sub alpha is a subgroup of G. So what this is saying then is that the intersection of subgroups is a subgroup. There's a quick way to summarize it. And notice this is any family, so this is not necessarily a finite family, it's not even necessarily a countable family. Any collection of subgroups. When you take the intersection of that collection, you get a subgroup. So for the proof, I'm going to use the subgroup test. So first thing we need to do is make sure that we are non-empty, right? So since H sub alpha is a subgroup of G for each alpha in script A, we have the identity is an element of H sub alpha for each alpha in script A, right? If you're a subgroup, you got to have the identity. Now, what does that tell us? Well, if E is in every one of these H sub alphas, that means that it lives in the intersection. So it follows that E is an element of the intersection alpha in script A, H sub alpha. And so the intersection is non-empty. Okay, so let's see, we've got non-empty. Now we need to show that it's closed under multiplication and under inverses. So let's let, say, X and Y be in the intersection. So that's going to be intersection alpha in A, H sub alpha. So now, given any little alpha in capital A, we have both X and Y are elements of that particular subgroup H sub alpha. And then using the fact that H sub alpha is closed under both products and inverses, right? So since H sub alpha is a subgroup of G, we have X, Y is an element of H alpha, and X inverse is an element of H alpha. So here I'm using the fact that H alpha is closed under multiplication and inverses. It follows right? So what did I do? I chose at random, right, an arbitrary alpha in script A, and I showed that xy and x inverse have to be in that h sub alpha. Right, so it follows that xy is an element of the intersection and x inverse is an element of the intersection also. So that completes the proof, because what we did, we just applied the subgroup test. So by the subgroup test, by the subgroup test, intersection alpha in script A, h sub alpha is a subgroup of G, right? So that's the end of the proof. For those of you that have never seen that symbol before, the script A, right, it's basically that symbol right there, right? I learned that one long ago, and I kind of like it, so I sometimes use it. So there's the script A. In fact, you'll probably see it later on. If you had me for Math 248, you've probably already seen me use the symbol. But anyways, that's the script A. Okay, so what's next? Okay. Now, remember what we had when we defined the subgroup generated by little g. You don't need to write this down, we already have this, but it's the set of all possible powers, say g to the I, where I runs through all integers, right? So it's all possible powers of little g. What we want to do is generalize this, so instead of having a subgroup generated by a single element, we'd like a subgroup generated by multiple elements. Yeah, I'll use this as a definition. So let's let G be a group, and let's take a subset of G. So S is a subset, not necessarily a subgroup of G. It can be, but all we need is for it to be a subset. Now, the subgroup of G generated by capital S is, and we'll write it as angle bracket S, and it's going to be the intersection of all subgroups of G for which S is contained in H. So there's the definition. Notice that there's nothing to prove here. This is a definition. And what we did, we showed earlier that any intersection of subgroups is a subgroup, right? That was our previous theorem. And so here, the subgroup of G generated by this set capital S is automatically a subgroup, right? Because what we're doing is we're taking all possible H's that contain S and intersecting them together. Right? So it's automatically a subgroup. There's nothing to prove in terms of whether it's a subgroup or not. Now a little bit of terminology. So if G is a group and S subset of G is such that the subgroup generated by S is equal to G, then S generates capital G, and what else? a little bit more, and each element of S is a generator. One more piece, or one more word that we'll use. So in the case that capital S is finite, then we say that capital G is finitely generated, right? So if there is a generating set that's finite for capital G, then G is finitely generated. So in the case that S is finite, we say that capital G is finitely generated. Now, this definition, it's nice in one sense. There's nothing to prove, right? It's automatically a subgroup. But now the question is, and here's maybe the downside of this definition. We created this thing called the subgroup generated by S. What does it look like? I mean, we know it looks like an intersection, but who are the elements? What do they look like? So we're going to need to get a characterization of that. A couple of observations, though, before that. So observation, or I guess observations. Number one, note that the subgroup generated by G is equal to capital G, and so what that tells us is every group has a generating set. This is not particularly interesting, right? So it's not a very efficient generating set, and in many cases that's what we're actually after. But it is true that the subgroup generated by G is equal to G. Also, the subgroup, no, what do I want to say? Sorry, the subgroup generated by the empty set, that's equal to the trivial group. All right, so there's a couple of facts. And now, we're going to move on to a theorem that gives us a handle on what the subgroup generated by a particular set looks like. So, so this is theorem 7.2. So let's let G be a group, and if we take a non-empty subset of G, we already know the empty set generates the trivial subgroup, so we want to look at a generating set that's not the empty set. Then the subgroup generated by S is equal to the following set. So it's equal to the set of all things in the form S1 to the N1, S2 to the N2, dot, 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 Sn, Sk to the Nk, where the Si's come from S, and the N sub k's come from integers. So this is a much nicer characterization of the elements that live inside the subgroup generated by S. What do they look like? They look like products of powers of the S's. Take all possible expressions that you can form that look like this, and that's going to give you all the elements in the subgroup generated by S. So in fact, let's do a little bit of a paraphrasing here. So that's the end of the statement of the theorem, but before we do the proof, so the subgroup generated by S is the set of all products of powers of elements, powers of elements of capital S. Right, so there's a way to sort of think of what this set script S looks like. Sorry, angle bracket S. So now for the proof. And what am I trying to do? I'm trying to show that the left-hand side equals the right-hand side. And so here we go. I don't want to have to keep writing this right-hand side out, so let's make a symbol for that. So let's write, I'm going to use the symbol capital A. So let's let A equal the right-hand side there. So that's the set of all things of the form S1 to the N1 dot 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 SK to the NK, where SI is in S and NK is in Z. Okay, so I need to show that angle bracket S is equal to capital A. So now let's let H be a subgroup of G that contains capital S. So such that capital S is contained in capital H. Now, if we take let's say if S1 up through S sub what symbol do I want to use here? N, S sub N. If we take some elements of capital S and some integers, so and N1 up through, how am I using N, really? Okay, I can't use an N here. Change this to a T, how about? So then I can use, I just didn't want to use N sub N, that would not make sense. So N1 up through N sub T are elements of Z. Then what can we say if we take an element that looks like this? Where does that element have to live? So then, what does that mean? So it means that S1 to the N1 dot 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 SK S sub T to the N sub T. So what do we have here? We have S1 lives in S, which means that it lives in H. S2 lives in H. S3 all the way to ST. All of those elements live in H, which means that their powers live in H because H is a subgroup, it's closed, which means that when we multiply all those elements, this lives in H. So what does that mean then? It means it means that A is contained in H. So it follows take all such elements, that makes up capital A, and so all elements of A live in H. So it follows that A is contained in capital H for all subgroups H such that S is contained in H. So every possible subgroup of G that contains capital capital S must contain A. Therefore, therefore what? That means, right, that means that A is contained in the subgroup generated by S. So why is that? Remember the definition. The subgroup generated by S is the intersection of all subgroups all subgroups of G that contain S. So if A lives in every one of those subgroups, that means that it lives in the intersection of those subgroups. And this right here is the intersection. Okay? All right, so what I have is containment in one direction. I have that A is contained in angle bracket S. Now I need the other way around. So, oh, yeah. So let's say now, note that A is not equal to the empty set. And the reason, if you remember what we wrote down at the beginning, we had that S was a non-empty set. Right? So if so what did I say here? Oh, right. S is a subset of A. And so that tells us then that A is not empty, right? Because we know S is not empty. I guess I should say a reason. So here, because non-empty set S is contained in A. Okay, so now think about elements of A. So also observe that A is closed under products and inverses. It's basically by construction, right? If I take two objects that look like that and multiply them together, I get an object that looks like that. If I take an object like this, then its inverse is going to be obtained by just changing all of those exponents to their negatives, right? Which is another object that looks like this, right? So by construction, A is closed under both products and inverses. And so what I just do, I just use the subgroup test. So A is a subgroup of G. So now what do we know? A is a subgroup of G. So now we have A, subgroup of G, where S is contained in A. Now, what do we know? The angle bracket S, this is the smallest subgroup. It's the intersection of all subgroups that contain S. Well, A is one particular subgroup that contains S. Since A is a subgroup that contains S, that tells us that angle bracket S has to live inside A. So therefore, angle bracket S is contained in A. Right? That gives us equality. And so that's the end of the proof. Okay, so we're going to stop here. I'm going to start a new chapter with the next lecture. And this lecture is a little on the shorter side. What is it, 23 minutes? So, okay, so that'll give you a little bit of a break. This is, I think, Thursday's lecture. What do I want to say? Okay, enough for today. We'll see you next time.